Okay, so like I said, this is a question that's very unique. They don't give us any numbers and we're trying to solve for this speed. Okay, so what we're looking for here is what's happening at each point. So let's start with at point A. Okay, at point A we have m times g, and my h is 4 times r. Okay, and then this says released, so I'm going to assume it has 0 plus 0. That's my kinetic energy. Okay, so I have my potential energy plus my kinetic energy. Okay, so there we have the first point. And this is going to be used and set equal to any other point. So now let's look at point B. So we're going to have, that's A, and that's going to be set equal to the energy at B. Okay, so B is also going to have potential energy plus kinetic energy. Okay, but what do we know about the potential at B? Is it's on the ground, so that is going to be 0 plus 1/2 mass times B squared, and that's what we're looking for, right? So if we're trying to solve this, okay, we have a mass here, we have a mass there, so those should cancel out. Okay, so I have G times 4R equals 1/2 B squared. Multiply both sides by 2. If we're multiplying 4 by 2, we get 8 G R. Okay, we're going to square root both sides. Okay, so that is the velocity at B. Okay, now on to part C. Mg4r equals, okay, now it has a height. Looks like it's a height of 1r up. Okay, so we're going to have m times g times r plus 1/2 m b, and this is at c squared. Okay. All right. So going forward from here, what can we do? Well, everything in there has a mass component in it, so we can divide everything by mass. So what we're going to do is going to get g times 4r equals g times r plus 1/2 b squared. Okay, now we could subtract gr from each side. Okay, if we have 4 grs and subtract 1 gr, we get 3 gr equals 1/2 b squared. Multiply both sides by 2. Take the square root. And that was the velocity at C. Okay. Before I get to the velocity at D, notice E is at the same height. Okay. So if E is at the same height as C, we can also solve for that one. Okay. Speaking of which, F is also the same height as B. Okay. All right. So let's do the last one then here. Velocity at D. So again, let's set this one up and try to show all our steps here. So we have our potential energy plus our kinetic energy equals our potential energy final plus our kinetic energy final. Okay, so we had m times g times 4r plus 0 equals m times g times, now that's at the very top, so there's an r and an r. Okay, and then this one is, well, we don't know, right? We want to have mv d squared. Okay, so I'm going to pull this for, well, okay, so we're going to divide everything by m. okay? So now we have that all done. I don't like that 4 in the middle. As you notice, I kind of drifted outwards. So I just rearranged, right? What's the word I'm looking for? Multiplication is communicative, right? It can be moved around. You can do it in any sequence you want, okay? So I just pulled the 4 and the 2 out front. Okay, so now I can subtract 2 GR from each side. If I had 4 GRs and I subtract 2 GRs, I get 2 GRs left. Multiply both sides by 2. Back to 4GR equals V squared. Okay, so I'm going to do the square root of 4GR equals V. Square root of 4 is 2. Okay, and that was at point D. All right. Speaking of which, we haven't talked too much about rolling inertia and circular motion. That's going to be a big part of this upcoming unit. Okay, so this is frictionless. Okay, and it slides down. Those are important words because rolling inertia messes with things. And if this does not go fast enough to make it around the loop, then I don't even know if we'd hit E. But all those things are assumed to be true for this scenario. Okay, and then I've deleted other parts of the question that would eventually come up. But this gives us the velocity at all of the different steps. Okay, all right, so that was quite a packet. Took us well over a week to finish it. Hopefully now you're feeling more confident. Hopefully you'll be ready to come into the test having set up all the questions in a similar manner. We take all the initial conditions and all the final conditions, and energy and mass are conserved, so we can just break it all up.